In the last two classes, we have discussed about the basics of an algorithm, and we also have discussed about basics of algorithm analysis, which is the process of estimating the resource requirement of an algorithm for its execution as a program. And in the last class, we have seen that if you want to compute an estimate of the time requirement of an algorithm, which can be computed as a function of the input size, and to obtain that, we have fixed the model of computation, which is a sequential single processor machine. And what we did was, we assumed that for every instruction the time required is a constant. For the first instruction, it is assumed as C1, a constant. For second instruction, C2, like that in an algorithm. And once we assume constant execution time for each statement, then we have to find how many times each statement will be executed. That is a repetition count. Then the repetition count multiplied by the cost of a statement gives us the time for that particular statement when the algorithm is executed. And hence the sum of such time requirements, that is product of cost into repetition count, gives us a method for estimating the time requirement. Today we are going to discuss about mathematical notation, which helps us in arguing about the resource requirement of an algorithm or of different algorithms for solving a problem, and thus can help a programmer in selecting the most efficient algorithm. And the topic for today is asymptotic notations. Before we look at the asymptotic notations, let us recollect the various levels of abstractions used in the analysis of an algorithm. If you recall, the first level of abstraction is assuming that each statement is taking a constant amount of time. Say for the ith statement, it is assumed as a constant Ci. Note that it actually depends on the machine in which that algorithm is executed, the machine speed and other factors, but the algorithm may be programmed and executed in different machines, and hence this is a necessary abstraction where we assume that the time for executing any statement is a constant. Okay, that is the first level of abstraction or assumption. And the second level is constant expressions representing the coefficient of a term in a complexity function Tn is abstracted away by replacing each constant expression with another constant. The statement may be confusing. Let us look at an example to see what it is. If you recall from the previous lecture, this is one of the time complexity function that we obtained. In the best case, the selection sort resulted in this formula, that is sum of constants multiplied by the input size n plus sum of another set of constants. And here we saw that we abstracted away this constant, which is a sum of many constant with another constant a. So rather than this summation multiplied by n, the summation is replaced with another constant a, and this summation is represented with yet another constant. So see that now there are two levels of abstraction. One is abstracting away the actual time requirement for executing a statement. For example, for the second statement we assumed it as a constant. That is the first level of abstraction. The second level is after obtaining the complexity value as a function, we can replace the constant expression like this with another constant to simply say that now the time complexity is linear in the number of input or the size of the input. A constant into n plus another constant. It's a linear function of on n. And today we are going to see a third level of abstraction where we can abstract away the constant associated with the higher order time. For example, here we may not be worrying about what this constant is, rather we will only look at this time, and which we can do by using what are called growth functions. Okay, we need to have a third level of abstraction. I will make it clear in the coming slides, and which is possible with what are called growth functions. Then what are growth functions and why they are used in analyzing an algorithm? So I am showing you here what a growth function is. It's the rate of growth or rate of change of a function t of n with respect to the increase in the value of n. So t of n is the complexity function. So rate of growth represents, suppose the input size is increased by some quantity, then what is the rate of change of the time requirement if it is the time? So that is the growth function, and here I am showing you typical growth functions used in representing the complexity of an algorithm. N to the power n, the graph grows like this, where if you increase the value of n, the function value, that is n to the power n, will be increased exponentially. Then n factorial, that means if you increase n, say from 5 to 6, the factorial value goes from 120 to 520. Okay, this is also a huge increase. Then 2 to the power n, the again exponential but better than these two. Say if you have now n as say 10, then 2 to the power n is 1024, but if you increase n to 11 from 10, a single increment happens for n, the input size, but you can see that the time requirement is doubled. It is 2048, or the growth functions can be n square or n log n, n log n and 1. 1 means regardless of the input size, the time requirement is just 1, and log n function grows like this, then n is like this, n log n, n square, likewise it goes. And from all these graphs, this is the complexity function that is the worst one, which is having the highest growth rate. The rate of change of the time requirement is highest among these functions for n to the power n. Let A1 and A2 be two algorithms for solving a computational problem. That is, we have a computational problem and somebody is giving us two algorithms A1 and A2 for solving the same problem. And suppose that the time complexity of A1 is this function and the time complexity of A2 is this function. Okay, then which one will be the efficient algorithm for that problem? Two algorithms are there for a single problem. You as a programmer, suppose you want to select one, which one you will select? Maybe you have to select the most efficient one. You can see that it is A2. Even though this constant is high, beyond some values of n, always this algorithm or algorithm with this complexity function is going to perform better than the other, because the rate of increase is more in n square. This is the n square graph, it goes like this. This is the graph for n. Okay, the growth is less in this case. So, the rate of change of time requirement is more for n square, and so the algorithm with this complexity function, that is A2, will be better. So, basically if you have a time complexity function like this, say 4n square plus 10n plus 10, which is a polynomial of degree 2, we don't have to worry about what this constant is and what all these low order terms are. You can just say that the growth function is n square. Okay, so from here we say that the growth function is n square, and for this we will say that the growth function is n, and based on this we can say which one is better. Okay, the better one is 1, then log n, likewise it goes. Okay, after obtaining the function, maybe a polynomial or an exponential function, we may not be worrying about these lower order terms. We will be only looking at the exponent, whether it is n square or n log n, likewise. And this is possible with what is called asymptotic notation. Okay, so that is the main topic for today. Asymptotic notation, which is a mathematical notation which helps us in representing the complexity of an algorithm using some mathematical functions. Okay, and these are used to abstract away the constant associated with higher order term and the lower order terms from a complexity function. For example, here you don't have to worry about this constant and also these two terms. You just say that the rate of increase is in the order of n square. Here it is in the order of n. You don't have to worry about this constant or whatever lower order terms are there in that function. And this is made possible with what is called asymptotic notation, and which can basically help us in representing the complexity as asymptotic complexity. And there are basically three types of asymptotic notations, and they are theta notation, biko notation, and omega notation. And I hope you have already studied about the basic asymptotic notations in your BTech. Anyway, we are going to recollect the definitions of these. So, what is theta notation? And now suppose that this is your time complexity function. Okay, the complexity function is f of n. Maybe you can say that that function is in the order of g of n under this notation. Okay, this is the function, actual function is this middle one, and then you can say that it is in the order of g of n when you can get an upper bound. Upper bound means you can have another graph which will always go above this graph, Lower bound means beyond a point always this graph will be below the original graph. Okay. So, this is a mathematical representation. Suppose you have a time complexity function f of n. Then if you can find a natural number n0 and two other natural numbers c1 and c2 such that the actual value of f of n for every possible value of n greater than or equal to n0. Beyond this point, you can see that it is both upper bounded and lower bounded by a constant factor of g of n. Okay. If you can find another function g of n such that when you multiply that g of n with a constant which will give you a lower bound for the function. Lower bound means if you substitute a value of n, this value is going to be less than or equal to the value of this function. Similarly, with another constant, you will get an upper bound. Okay. For example, if the function is this, you can say that it is in the order of n square. And if this function is linear, then you can say that it is theta of n. And when a function is in theta of g of n, that means function can be in the order of g of n, when this function g of n is both an upper bound like this and a lower bound within a constant factor. That is, if you multiply g of n with c1, then for every value of n, this quantity will be less than or equal to this quantity. That is, still this can act as a lower bound, can also act as an upper bound as a factor of another constant. I hope you are getting me. Basically, what I mean is that if you have a complexity function like this, then if you can find another function g of n which gives you an upper bound and a lower bound by like this, when you multiply that function with two constants c1 and c2, then you can say that the function f of n is in the order of g of n. Okay, it's both then g of n is both an upper bound and a lower bound. And if f of n is a polynomial like this of degree k, here it is of degree 2, you will say that it is order of n square. Here it is order of 1 because n to the power 1 is this. So, it is order of n under theta notation. So, in general, if this function is a polynomial of degree k, that is n to the power k, you will say that f of n is an element of theta of n to the power k. So, this is the complexity function. And some authors used to say that f of n is in the order of g of n, that is f of n is equal to theta of g of n. Even though this is the more precise way of writing it, some authors use this form. Okay. And when f of n is a constant function, like suppose it is a straight line like this, then you can say that it is in the order of 1 under theta notation. And why is it 1? Because it is n to the power 0. If it is a constant, then it is n to the power 0, and that is why you say that it is in the order of 1. That is a constant time. 1 doesn't mean that 1 millisecond or 1 unit of time. It means that it is a constant, maybe 1 hour or 1 year, that doesn't matter. Coming to the next asymptotic notation, which is called big O notation. So, big O notation is providing you an upper bound. Not that the theta notation provides you a lower bound and an upper bound. So, here it is just an upper bound. So, from this itself you know what is the definition. If there exists a constant c said that f of n is upper bounded by c into g of n, then you can say that f of n is in the order of g of n. For example, this polynomial in degree 4 can be represented as order of n to the power 4. And here it's a quadratic function. If you want, you can say that upper bound is order of n to the power 3. But it is not possible with the theta notation. It must be n to the power 2 because it must be both a lower bound and an upper bound. Here we need only an upper bound. So if it is a polynomial of degree k, it could be n to the power k or n to the power a number which is greater than or equal to k. And this is the notation, and this notation is good to represent the worst case time complexity of an algorithm. From the last lecture, you know what basically a best case analysis gives you and a worst case analysis gives you. If you recall, the selection sort in the worst case requires n square time, and in the best case it requires linear time, order of n. And some others say f of n is same as order of g of n rather than saying this. And when f of n is a constant, here again it is order of 1. Coming to the last notation, which is omega. Now from the figure, I think you are getting it. Omega is a lower bound, it gives a lower bound. So the definition tells you if you can find a constant c such that c multiplied by a function g of n is a lower bound for f of n, then you can say that f of n is in the order of g of n. Examples: this function, which is a polynomial with degree 4, you can say that it is order in the order of n to the power 4. Okay, and this is another polynomial in degree 2. Here you can say that it is in the order of n. And note that this is the lower bound. So if it is a polynomial of degree k, then you can say that it is n to the power k or n to the power a value which is less than or equal to k. And this is the notation. We can say that f of n is in the family of the function g where it is theta of g of n. Okay, maybe you can say that here it is order of n square or order of n. Okay, and omega notation is good to represent the best case complexity of an algorithm. Best case, that means always the actual complexity is more than this, or at least as it is greater than or equal to the value given by this function. Okay, this is the notation. And here as well, when the function is constant, then it is in the order of 1. And with this, we are finishing this lecture, and I am giving you some exercise problem. You look at this algorithm that we discussed in the first lecture to find the position of an element in a sequence, finite sequence. You look at that procedure or the algorithm that we wrote. You find the worst case asymptotic complexity, also its best case asymptotic complexity, and say which one of the three asymptotic notations among theta, big O and omega, which one is the most suitable for representing the time complexity of this algorithm, whether it is theta or big O or omega. Okay, and justify your answer. Then the last question is, how can you modify this algorithm to get a better best case asymptotic complexity? So given this algorithm, there is a best case complexity. How can you improvise that? Maybe you have to attempt some changes in the algorithm which gives you a more efficient algorithm in the best case. So today we have seen the basics of asymptotic notations which can be used to represent the resource requirement of an algorithm as complexity. and we have discussed the basics of three asymptotic notations: theta, big O notation and omega notation. Thank you.